Hey everyone, welcome back. So in this video, we shall take a look at some examples of autoregressive models. So, if you recall the autocorrelation function of an autoregressive process from the previous videos, right? It had this particular form, right? Correlation of lag h was phi to the power h. So we are going to study how an actual time series with this kind of a correlation structure might look like. So we generate two processes, right? In the first one, we have an AR1 model, which has phi is 0.9. In the second one, phi is minus 0.9, right? So if phi is positive, that is if it is 0.9, then all the correlations are positive. If it's minus 0.9, then like we've discussed last time, the correlations will swing from positive to negative, right, for successive lags. So we generate this process, and this is how the graph looks like. So this is autoregressive 1 with phi is 0.9, and you can see that this is smoother, right? And here phi is minus 0.9. So what it means is all the points, so basically if this point is positive, so phi of 1 is negative, right? So if h is equal to 1, minus 0.9 raised to 1 is minus 0.9, so that's a negative correlation. So if I look at my data at first time point, if it's positive, the second one is negative, right? So that's lag 1. Between 2 and 3, again, the correlation, there's a negative correlation, right? So again, if this is negative, the next one is positive. So you see that this data swings wildly up and down, right? It's because for lag 1, you have negative correlation. For lag 3, again, you will have these negative correlations. So negative correlation means if one data goes one way, the other set of points go the other way. So you see that this looks this oscillates a lot, and for positive correlations, this is smoother. So that is about positive and negative phi, right? So the sign of phi, even though it's an AR1 model, right, the time series corresponding to a positive and negative phi looks very, very different. So next we should take a look at explosive AR models. Okay, so what are these? So if recall random walk, right? So random walk, if you think, so this would be like an AR model with phi equal to 1. But remember, so far we are assuming that absolute value of phi is strictly less than 1. So it doesn't quite fall into those class of models. But you can see that this has a structure quite resembling the autoregressive models, right? We know that this is not stationary, right? So this is not an autoregressive model that we are considering yet, right? Because we're assuming that the autoregressive models are stationary and this one is not. But this makes us think that is it possible to have a stationary autoregressive, say, one process which has this phi greater than 1? Or absolute value of phi greater than 1. Is it possible? Does such a thing exist? Okay. So if you remember, again from the previous video, we can rewrite this AR1 process in this way. And the whole reason, right, behind assuming that this phi is less than 1 is so that this shouldn't explode. Because if this phi is greater than 1, you know, as you increase the powers, the numbers will get higher and higher. And that's where the name explosive or the word explosive comes from, right? So these processes with phi greater than 1, right, are basically explosive AR models. So let's see if let's look at this thing a little bit more deeply, right? So this is an AR model, right? Xt plus 1. So instead of xt t minus 1, I'm just changing the time points, right? So it's t plus 1, t wt plus 1. And right now, phi is I'm assuming that phi is greater than 1, okay? So this looks similar to the AR models we were looking at so far, but the phi is different in this case. Phi is greater than 1. Okay, so I can rewrite this. I just juggle some term around and then I can write this as xt phi inverse times xt plus 1 and this term. So now if phi is greater than 1, 1 by phi is less than 1, right? So we get this term. And then I keep on, basically if xt has this form, then xt plus, so if xt is phi inverse xt plus 1 minus phi inverse wt plus 1, xt plus 1 can be written as phi inverse xt plus 2 minus phi inverse wt plus 2, okay? So I'm looking at this structure but writing this in terms of xt plus 1 here, okay? So I get this term, I rearrange terms a little bit, and this is what we get. Xt is phi raised to minus 2, xt plus 2, phi raised to minus 2, wt plus 2, and then this term. So now you can see we're writing xt in terms of the future terms, right? And you can keep continuing in this way, right? So again, you substitute for xt plus 2, then xt plus 3, and so on. So if you do this k times, right, what you will get is phi raised to minus k, xt plus k minus this term here. So we can continue doing this infinitely, and ultimately this is what we get, right? So remember, if phi is greater than 1, phi raised to minus j is now less than 1, right? So we can definitely write things this way. So this would not be divergent, right? Phi raised to minus j's do not explode to infinity. They are controlled. So this model can be written. So this, we can show that this model is stationary. So that is good. However, it is useless because we're writing xt in terms of the future, right? So it requires us to know the future in order to predict the future, and it doesn't make much sense. So even though this is a stationary model, it is not very useful to us. So it's important to kind of keep in mind how we started with something that was explosive, phi was greater than 1, and we just rearranged some terms, and now we have this model which is stationary, which converges, which makes sense. However, I mean, it doesn't make complete sense because we need to know the future, right? So this is a thing about time series. You just rewrite terms a little bit, you get different properties, different interpretations, and so on and so forth. So when a process does not depend on the future, such as AR1 models with phi less than 1 or absolute value of phi less than 1, we say that the process is causal. So when the process does not depend on the future, this is an example of such a process. The process is causal. This here, if phi is greater than 1, it is non-causal, right? So what should we do with these non-causal or these explosive models, right? Should we just exclude them altogether? Should we just assume that autoregressive, assume the autoregressive models with phi less than 1? Are we missing out by excluding all of the conditions in which phi is greater than 1, right? Are we missing out by excluding an entire class of models? The answer is no. Right? So by excluding these explosive models, we don't lose out much because each explosive model, right? Remember, these are also explosive models are also non-causal. So each explosive model has a causal counterpart. What does this mean? Okay. So here is an example. This is an explosive model, right? Because phi is greater than 1. We know this is non-causal because when we rewrite it, it turns out that we have to write it in terms of future values to for the representation to make sense. So this is a non-causal explosive model, okay? And consider another model, YT. So YT, I'm saying, is phi inverse yt minus 1 plus vt. Now in this case, this coefficient or this constant beside yt minus 1 is less than 1, right? Because phi is greater than 1, right? This inverse is less than 1. And this vt, so in this case, vt was white noise with this variance structure, and here it is still white noise, right? Or it's more specifically, it's a normally distributed variable. The only difference is its variance is a bit different. But this is a legitimate AR1 process, right? Yt depends on what happens one time step back. This constant here is less than 1. This is IID, normally distributed random variables. So this is an AR1 process. This is also causal, right? This is a causal process. And we can show that, right? We're not going to show this right now. We'll get to this point later. But it can be shown that xt and yt, so these two processes, are stochastically equal. What do I mean by stochastically equal? What I mean is both of them have the same finite dimensional or finite distributions. So what does that mean? So if I take some set of m points from x, and if I take this same time points of y, that is if I have these two sets, so these sets of variables have the same distribution, okay, regardless of the time points and for any value of m. So if I take x at times t1, t2, t3, and if I take y at times t1, t2, t3, these two sets of variables have the same distribution. Okay, if I take x at time t1, t2, if I take y at time t1, t2, these two sets of variables have the same distribution. Okay, it's something, so even though x is explosive, right, for each such explosive x, we have this causal y, right? So this fits into the framework of things we have been studying so far. So for each x, we have a y such that the two have the same, such that they're stochastically equal, okay? Again, to clarify this idea of stochastically equal, if you take two, if I have x has a normal distribution with 0, 1 and variable, let me not use xy. Say if there's a variable v which has normal distribution 0, 1, there's another variable w which has normal distribution 0, 1, then they are stochastically the same, right? Even though they're two different variables, they have the same distributions. It's the same idea extended here. So basically, we are not losing out by excluding this class of models, right? Because for each of this model, there is something, right? There is a parallel or there's a counterpart in this causal models that we are considering. So basically we can exclude them from consideration. So we can exclude these explosive models, right? We are not missing out much by excluding them. So that's all about AR models. In the next video, we shall be revisiting the moving average models. See ya.